Hey there everyone, it's Alejandro. Welcome back for day 311 of me doing Daily LeetCode Challenge after it's 1 year's worth of green contributions here on GitHub. So today's from May 23rd, 2025. Without further ado, let's get straight into it. Okay, today we get LeetCode hard. Problem 3068, find the maximum sum of node values. There exists an undirected tree with n nodes numbered from 0 to n minus 1. You're given a 0 index to the integer array edges of length n minus 1, where edges of I is equal to ui vi. Indicates that there is an edge between nodes ui and vi in the tree. You're also given a positive integer k and a 0 indexed okay. Index array of non-negative integers, so 0 or positive, like that, where nums of I represents the value of the node numbered I. Okay. Alice wants to find the sum of the values of tree nodes to be maximum, for which Alice can perform the following operation any number of times, including 0 on the tree. Choose any edge uv connecting the nodes u and v, and update their values as follows. Nums of u is equal to nums of u x or k, nums of v. Wow, okay. Well, the trivial way of doing this is essentially go through every single possible permutation. You essentially want to pick the valid subset. Okay, oh boy, I see. So basically you have a bunch of edges, and for each one you want to say, do I apply the operation or do I not, right? So that's kind of the idea. How many edges are there? N minus 1, where n is up to, 10 to the 4 means it's going to need to be linear on the size of the edges. Maximum sum, yeah? Now the only thing, maybe there's a greedy way of doing this, right? Now the only thing is if you do it with uv and vw, then nums v becomes nums v xor k, which is just nums v. So really every single number has one of two possible values. That's an important distinction, and probably something that we're going to abuse, right? XOR is probably not something that is random here. That means that every single number in the end of the day will end up having one of two values. We want to select essentially the best subset, right? Shoot. It's just, I always forget how to solve these types of problems, right? Like, return to me the best subset that does something. Which is like, usually DP, but here it's like, you need to remember the internal state. We solved a problem like this a couple days ago. I already forgot because I'm a dumb sometimes. Okay. Okay. There's something like DP here, so if we treat each edge as something that we have a choice for, right? Apply or don't apply. The only problem is that you end up changing state, right? Like in DP, it's nice when the subproblems are recursively related to one another and you don't change some global type of state. Unless it's like, if you apply it, right? Or maybe we could do a DP where it's like we get the difference of what happens when you XOR the value, right? Because the thing is, like, let's say 5 becomes 3 and 3 becomes 5. The point is that you end up doing -2 at some points and +2 at some other points. But then you have to know whether or not you've XORed every single node, and then it doesn't become efficient in terms of time. Oh boy, okay. I mean, something like maximal subset Is that an NP complete problem, right? Because a problem like subset sum is already NP complete. Well, a problem like maximal subset, it wouldn't make sense, right? You just pick all the numbers that are positive, and yeah. But something like subset sum specifically is NP complete. So like the idea of grabbing an optimal subset is not something that's like, you know, generally doable with I don't know, right? That's not something I can't say that you don't do generally with dynamic programming, right? Because obviously dynamic programming is really good in subset problems where you aggregate to some value, right? Here it's like about sum, but like the point is that whenever you commit to a decision, you can't encode that extracted value directly so that you keep the right? It's like if you choose to go along, like for example, when you do something like shortest path, right? If you choose to go through an edge, then it's just like, okay, you've augmented your current path by 1, right? But you haven't changed the state of the graph. Versus something like this, it's like if I lock in a decision like to utilize an edge UV, then I do change the state of the graph. I change nums u to be nums u XOR k, and same thing with nums v, and that's a problem. Right, an obvious greedy solution would be like, you know, go through all the edges, and then it's like for each one, be like, does it augment the score, right? But it also, it's like, you know, we're obviously going to fall into a trap where it's like nums of u XOR k. Like let's say we say, oh, uv is not valuable because we make v so bad, right? But then there's another edge vw, and it just cancels the effect. So, yeah, greedy is not going to be fun here. Jeez, okay. Yeah, I'm already starting to tell why this is a hard. Let's look at some examples, if anything. 1 to 1, k is equal to 3. 0 to achieve a maximum sum of 6 using a single operation. Choose the edge 0 2. Right, okay, like the point I'm trying to illustrate is that, like, you know, we could easily solve this via like something like backtracking, right? The point is that it's obviously going to be too slow, but obviously, right, correct but slow. I mean, backtracking is just brute force, but might as well. It's an okay starting point. Oh gosh, okay, max sum. Infinity. Res, return res. R is equal to this. Well, actually, we'll say for sum. Actually, we'll just do def backtrack of I. And comma m equals length of nums, length of edges. Let's grab this value. Then we'll just say res equal to max of res and sum of nums. We're gonna be able to optimize that after. For now, I don't care. And an important return here. Otherwise, we'll say we're not at the last index. So, case 1. Don't apply edge. So, backtrack 5 plus 1. Case 2, apply edge. Alright, so here we'll say nums of equals edges of I. View XOR equal to k, nums of v, XOR equal to k, backtrack I plus 1, and then undo. Nums of u x squared equal to k, nums of v, x squared equal to k. Turn res, right? So something like simple like this. Well, it won't work because we haven't called backtrack yet. Backtrack of 0. Oh boy, non-local res. Yeah, so something like this is obviously accepted. Now the only thing is, yeah, I could keep track of a current sum, right? So okay, obviously something like this is gonna TLE, right? But the point is that it's correct, right? Correct, but TLE. So just run it. So the difficult part of this problem is obviously solving it efficiently and not actually solving it. Okay. Now we can just do something simple. Cur sum is equal to sum of nums. Max of res, gamma cur sum. Here we'll say old u, old v is equal to nums of u, nums of v. And here we'll just say cur sum. There's money. We're gonna say cur sum. So if nums of u is smaller, we want to subtract cur sum. So we'll do nums of u minus old u, as well as cur sum plus or equal to nums of u minus old v. And here we'll just do minus or equal, and nums of u equals old u, nums of v equals old v. How about something like that? Non-local cur sum. No. Nums of v, that would be quite important. Okay, so that's accepted. So now we don't have to do O of n work, at least in here, every single time. So here we pass 353 test cases. Let's see if we pass a little more, but still most definitely TLE. Oh, now we just get a wrong answer, straight up. Oh, what is this? Oh, because it's the, yeah. Let's reverse the process here. Yeah, my bad. Obviously, like, otherwise this is just old u and old u. Okay. Yeah, so TLE, although it seems like, yeah, we're just at 353 out of 718. This is bad. So we obviously can't go exponential on the size of edges. Okay, so now the question is, how are we going to solve this efficiently, right? There's definitely this idea that we're going to be able to leverage, which is the fact that each number is basically, it can only possibly have one of two numbers. It's almost like a matrix, right? It's like toggling. It's almost like could we convert this into a problem where it's like essentially we start off with like a binary number, and for each for each number nums, do we say 0 if it's already at the max number can be, or 1 if flipping it would make it bigger, right? And or the other way around. Like in that example, then it's like, okay, what's the smallest number I can get? And then it just becomes like a path traversal, right? Where the cost of a path actually, that's a pretty cool way of approaching it, right? But then the number of paths is exponential. That's the problem. Yeah, because I'm dealing with an exponential graph here. Because the graph isn't just like the nodes and edges given to this problem. It's the, do you make a decision here or do you not make a decision here? Kind of a graph. I can't do that. That's exponential. There's got to be some way of graph reducing this. What's the percent acceptance rate? Oh, 65 is not bad at all. Okay, maybe I have to think about this a little harder. First of all, this is an optimization problem, which usually means we can either solve it with dynamic programming, greedy, or divide and conquer. If the acceptance rate is this high, I wonder if there's like a greedy way of just approaching this, right? Yeah, I don't know. I don't like greedy here. Definitely some way to I don't know. Like right now, like any graph reduction method I'm thinking of is just exponential, which is just not okay. Well, maybe something is like, you know, why are we given nodes and edges, right? Can we traverse the graph and get some type of information? Oh, wait, that's exactly what we can do. Every single time we unlock an edge, this is how much it affects our sum by. Ah, I think I understand. We can find the highest yielding cost path. Yes, yes, this is exactly what we can do. Oh, this is gonna be so cool. This is gonna be so cool. We can grab the sum of nums as our starting point and then be like, okay, what is the path in the graph G that yields the highest cost, right? Or like, you know, the maximum sum. So in that case, I guess it's like, you know, minimum. I mean, at this point, I could just do everything negatively. The only thing is that I won't have gold nodes, right? I just hope that there's no infinite cycle cost paths. Now, the only thing is I can't do something like up air shortest path. But does it really matter the node I start from? No. Or maybe it does. Oh gosh, I can't start from every single edge node, can I? Yeah, n squared is too slow. Like if I run a UCS or BFS or DFS from every single node, each of which has n-1 total edges to explore, that's too slow. If this was 1,000, that would be nice. Oh, a valid tree. Oh, it's a tree? Oh, it's a tree. Oh, it's not a random graph, it's a tree. Oh, buddy boy. Well, that's definitely not random. Haha. Now the only question is how the hell do I find the root of this tree? Me gusta mucho, me gusta mucho. Ah, that's annoying that's... I wish the edges were directed so that, like, you know, we could just run a topological sort. Yeah, we've done these types of problems before, right? Where it's like a tree. Are we given like some guarantee that the root is always like rooted at 0? I won't be able to assume this, will I? No. Well, the thing is, what I can do is for each edge, there's really two ways to go about it. I either include it or I don't. Yeah, but this greedy stuff. Ugh. Do I need something like Bellman Ford here? I definitely like this idea of deltas, right? Maximal path. Well, I could for each path, like, you know, keep track of set of visited nodes. So it's getting a little messy. Now, the very first thing we're going to do then is backtrack solution. TLE. There we go. And we'll do this. Okay. Now we'll say adjacency list is equal to I points to an empty list, in range, and for u comma v and edges, adjacency list of u. I'll make this a set just in case. Dot add v, adjacency list of v dot add u. Right. Oh, now the only thing, yeah. Now the cost of the edge. But the problem is that you modify state, right? Def edge cost, get edge cost, edge, u comma v equals edge. U modulo k, so v modulo k. Is equals 0. Res plus or equal to new u minus old u, new v, return res. Get edge cost, comma v, edge cost, edge cost. Okay. Want to find path with maximal sum in graph. Now, how do we do that? For now, let's start 0. We don't even want path, right? Something like this can't be right. Yeah. Yeah. It's like you toggle the twos. Actually, what we could do is max heap is equal to this. And get everything's initial edge costs. For u comma v in edges. Also, let me disable flux. We'll say, let's grab the edge cost. Heap u dot heap push. Will be this u comma v. Edge cost u comma v. Heap q dot heapify max heap, because now this will be O of m. So let's do things that way. Max heap. This will be negative. Edge cost will be equals heap q dot heap pop from the max heap. Edge cost equals negative edge cost. Get edge cost u comma v. Then heap q dot heap push max heap the correct value and continue the for loop, right? The while loop. Otherwise, let's apply it. Let's try to be greedy and applying the most beneficial edge costs first. Otherwise, res is equal to sum of nums initially. Let's say res cost less than square 0, break. Nothing good for us anymore. Assert false for now. Otherwise we'll say res plus or equal to maybe we'll have like, you know, a visited again thing, and then it just eats it up. Okay, for now let's just do return res. No. Rescene. Rescene. Break otherwise. Interesting. Okay, for now, let me just do okay. It's weird because basically from the tree, exactly 2 amongst each path will be chosen, right? There's many ways to go about this problem. Okay. Here, what happens if we just break? Interesting. I'm still wrong. Don't break here. Really? Okay. So you could change state. I wish like I could capture this change state in like a graph. It's like if you choose to select the node, the edge UV, you get this many more points, but now all of a sudden here's the new graph state that you have to deal with. Which is literally just backtracking. Oh gosh. Okay. In that case, we can probably utilize some of the hints, right? I think we're at a point where we've tried, you know, a valiant enough attempt, and it is time to just, you know, use the hints to help us move forward a little bit. So you know what? I'm going to get straight into it, starting with hint number 1. Select any node as the root. Okay, sweet. That's a cool thing you can do. I was gonna, just pick 0. I was worried that, like, maybe it's one of those where you need to do a null path. Get the best path from every single node, which obviously is not possible from the constraints. So, okay, cool. Hint 2, let TP, okay, so this is the DP problem. Let TPXC be the maximum sum we can get for the subtree rooted at node X. Oh, we're abusing the fact that this is a tree, okay. I see. Yeah, that's what I was saying earlier, right? There's only going to be ever 2 that are selected in a path. Or no, that's not even true. Interesting, okay, hint 3. Wow, okay. Right, yeah. Okay, I'm going to look into the discussions here. Nice, okay. Well, all nodes connected? Oh, because it's a tree. I see. So edge UV is kind of like a trick. You can really pick any 2 nodes. Ah. That's so silly, right? Oh boy. Okay, wait. Attempt. At my attempt at solving this problem before checking out hints and discussions. And now we'll just do this. Come on over here. Get rid of the word attempt here. And just say, this is going to be actually a really clever thing. Delta x or k minus none. Delta is greater than 0. I guess I could do greater than or equal to 0. Right? Well, really, I could just add the deltas. Right? Because as long as I pick 2 at a time and it makes sense to do so, then it makes sense to do so. Non module k minus none. Heap q dot heap push into the max heap. Delta comma none. It'll be this. Or num and nums. This negative. Come on now. we'll say max heap 2. Two goes here. Okay. 1 plus delta 2. Or we could just say greater than 0. Then we'll confirm that edge. But the only thing is that we end up changing nums2 and nums v. Okay, wait. Yeah, no, but that's a problem. No. We can do it between every single 2 nodes. Where we just end up never picking it again. Right, yeah, that's the point. We just end up never picking that node ever again. We leverage the fact that since this is a tree, that means every 2 nodes are connected, which means we can apply an operation on any pair of 2 nodes v in the graph, not just the ones in edges. Okay, and now this is me confirming. Is initially equal to sum of nums. Supposed to equal to delta 1 delta is equal to delta 1 plus delta 2. Return res, something like this. Keep it 5. No, not even close. It's because there's cases where you can have transitive, right? If you have UVW, otherwise Okay. No. Interesting. Yeah, interesting. Okay, let's keep reading that guy's discussion comments. Yeah, this is actually really here. Yeah. Yeah, so with that we can essentially XOR any two nodes. But why can't I just grab like a hold of the deltas? Well, it feels like something like this is just something I could do. I don't know why a solution like this doesn't work. Yeah. Yeah, basically. Like, what? Then why doesn't this work? Get delta is lambda none. One modulo k minus none. Negative get delta none. Actually, it's simpler than that. It's deltas Something like this. No. Yeah, so this is exactly what I was doing, right? Yeah. But this doesn't even make any sense. String min delta equals plus deltas just in case. Sorted. Ah. Delta is not associated to a single num, it's associated to two. Right now. Get string get delta of num equals get delta of num. Num modulo k num equals num. Oh my gosh, it's XOR, not modulo. Oh my gosh. Yep. Delta's greater or equal to 0. Okay. Dang. Okay. Boy, am I close. Res equals max heap equals some nums equals so ideally what we do is we take this, take this and this. Yeah. Let me increment my brightness. Yeah, so I like the heap idea. Negative delta num for num and nums. Yeah, this condition can go bye-bye. And now we have got a working solution, don't we? Yeah, boy. Yeah, boy. Okay, wrong answer. Let's figure out why. Yeah, so here we don't necessarily want to break. -6, 2, -2. Clearly we want to just add 8. That's not what's happening. Delta 1, delta 2 equals. Well, ain't that funny? Do. Oh, I'm dumb. I did it. Oh my gosh, I'm actually so dumb. Now we're chilling. Yeah, now we're chilling. Oh my gosh, that's so silly. Okay. And there we go. Bada bing, bada boom. Completion streak 311 days. Consistency is key. See ya tomorrow. Wow. Okay, this problem is actually so trivial. when you just realize the trick. That's actually kind of humble. It's actually kind of sweet how that works. All right. Yeah. Here we can get rid of all of our beautiful print statements. Yeah, here we can get rid of this.
I folded something, I gotta put it, they don't fold.
Yeah, here what we can do is negative delta. Delta 1 equals this. Delta 2. If delta less than or equal to 0, break. Otherwise, res plus or equal to delta. And then just return res. Booyah. Okay. Submit. See how that is now. Okay, 24.14%. And we can do a little bit better if we do negative of this. And even instead of that, we can just do it the other way. Yeah. Num minus this. And now it's just even better, right? Yeah, so. So here we'll just say num minus num x to k. Delta comma num. Or faster of operations. Of one operations. Submit. Damn. Really? It's slower with num minus num modulo k? Okay, there we go. 63.79%. That's exactly what we'd like to see. Bada bing, bada boom. Okay, so nevertheless, as always on my videos, I do a quick recap of various problems. For this one, we did end up needing to look at the hints and the discussions, and the one that really helped me out was this one over here. At some point I was stuck with the problem because I was actually doing modulo instead of XOR, and I was like, why the heck is this not working? This has to work. Why is it not working? I was using the wrong operation, so that's a silly me kind of moment. But this is the trick that helped me. So in this problem, essentially, we're given very important fact, a tree, not just a graph, but an undirected tree with n nodes numbered 0 to n minus 1 and a bunch of edges ui, vi. Now, nums is a function, is an array where nums of 0 is essentially the value of node at index 0, nums of 1 is the value of node with label 1, yada yada yada. And essentially what we want to do is pick the maximum sum of the node's values that we can get, where the operation that we're allowed to apply is essentially as many times as we want. We can choose any edge uv from edges and say, hey, nums of u, we're going to XOR it by k, and nums of v, we're going to XOR it by k. Now, the very first thing to notice is that when you XOR nums u, let's say we XOR nums u with k, right? One thing to notice is that any number you grab, right, any number x, if you XOR it by some other value y, and you XOR it with that value y again, then this is the same thing as this in parentheses. Any number XORed with itself is just 0. Any number XORed with 0 is just itself. So when you XOR a number by the same number again, it essentially nullifies the effect. So if we XOR nums u with k, and then we XOR it with k again, it essentially becomes the original nums here. Now the reason this is important, and this is something I realized at the beginning of the problem, but this is what I didn't realize, is that essentially this allows us to not only XOR any two nodes in edges, but any two nodes inside of the entire tree. Because since this is a tree, that means that every single two pairs of nodes is connected to each other inside of the tree via a path. And what we can do is that no matter how long the path is, right? Let's say we have node 1, 2, 3, 4, n, right? Let's say we want to XOR essentially the values of nodes 1 and 2. Well, what we can do is we can XOR 1 and 2. We can XOR 2, apply the operation on 2 and 3. We can apply it on 3 and 4, all the way up to, you know, n minus 1 and n, right? So what happens here is that we XOR the value at number 1 by k, as well as the one for number 2, right? So here's like we've XORed the values for number 1 and number 2. Now when we do 2 and 3, we XOR the one with label 2 with k again, which means it nullifies its effect, and 3 here is XORed for the first time. Then we XOR 3, which means this one gets nullified, as well as XOR 4, so this one gets here, right? And the point is we keep nullifying over and over and over until we get to this one, n minus 1 and n, where, like, you know, n minus 1 will get nullified and n will not, right? So since this is a tree where there's a path between every two nodes, we can essentially abuse this mechanic and allow ourselves to XOR any singular two nodes inside of the entire tree. Now, using that information, what this allows us to do is be like, okay, we can essentially XOR any two nodes that we want in the tree at a time. Let's do it only for pairs of nodes where it's advantageous to us, right? So what we can do is essentially compute the reward for XORing a node value by k, right? Which means that if I, so, sorry, I'm gonna drink some water. If we XOR a number by k, right? Let's say we have a number and we turn it into num modulo k, then what is the reward of doing so? Well, it's going to be their difference, right? We turn num into num modulo k, so the difference will be num modulo k minus num, right? This is the reward of essentially turning num into num modulo k. Obviously, if this whole sum is negative, then that means we actually went smaller in number, and that actually harmed us, right? Because we want to maximize the sum of the nodes after we apply as many operations as we want. So this kind of gives us a little bit of a reward function, right? Which essentially, if we were to XOR a number inside of nums by k, then this is essentially the reward we get for doing so. So our initial sum is the current sum of nums, right? And then we can keep applying rewards. And so the way we apply rewards is, well, we must apply a reward on two nodes at a time, right? So, like, you know, for any edge UV, we must do it this way. Well, we realized by these operations, we can essentially apply this on any two nodes in the graph at a time, not just any two nodes inside of edges. This is actually kind of like a red herring to this problem. And so what we can do is essentially say, hey, how about for each node, for each number, let's keep track of its reward inside of a max heap, right? So that we essentially have a max heap with the maximum reward of applying an operation on a node. So that's exactly what I did. Is here I called it get delta, which is equal to lambda num modulo num XOR k minus num, right? That's the reward here. And then here we do negative get delta of num for each number in nums, right? Negative because we're simulating a max heap via min heap. Again, if you don't know this trick in Python, essentially in Python you have access to the heap queue library, which is a min heap, right? So that means if you have something like 1, 2, 3, when you pop something, it'll be 1. But if we were to turn every single number into a negative number, then all of a sudden the smallest one is negative 3. So when you pop that from the min heap, then we can just remultiply this by a negative 1, and there we go, we got the original number 3. So you essentially simulated a max heap via a min heap in Python. So that's why I multiply every single number by negative 1 instead of by max heap. I get delta num. But just for the sake of faster of one operations, I was like, okay, we want the negative of num XOR k minus num, which is just num minus num XOR k, right? Again, I was just doing this for faster of 1, but this is the exact same idea. So I grab this max heap and keep q.heapify it in O of n time, right? Then what I do is like, okay, the current sum of the numbers is what my current sum is, right? Now what I'm gonna do, essentially I'm gonna go through my max heap, and I'm gonna say, okay, I can essentially apply 2 rewards at a time, right? Because here inside of my max heap, I essentially have the reward for every single unique number, which represents every single unique node inside of my graph. What I can do is I can grab the 2 highest rewards, and if the sum of those rewards happens to be positive, then that means I could essentially XOR those 2 numbers and essentially yield a greater total sum. So that's exactly what I do. I say while the length of the max heap is greater than or equal to 2, as long as I at least have 2 things, 2 numbers to essentially get rewards from, let's pop the maximum reward, which is delta 1, is equal to negative heap pop. Again, remember what we were doing. We're simulating a max heap via min heap. We got to remultiply the number by negative 1. So delta 1 is equal to negative. So you know what? If anything, like I should call this like, get reward, and this is like reward 1, reward 2, just by the way I'm explaining it, but here I call them deltas. Well, essentially, this is the reward of the best reward I can get and the second best reward I can get, and so the total reward is the sum of these 2 rewards, right? Now, if the reward or the delta here is less than or equal to 0, that means it's either gonna harm my total sum or do nothing to it, in which case it's like, and there's no better reward because here we picked like, the 2 largest deltas inside of the max heap, so everything else is just gonna be equal to this or worse. So if our current, reward is non-influential or harmful, then we just break out of this while loop because we don't need to consider anything else, right? Otherwise, we're gonna add that reward or delta to our result because essentially we apply that reward on both numbers. Now, notice that one of the deltas could actually be negative, right? It could be that XORing one number gives a reward of 5 and the other node a reward of negative 2, so the overall reward happens to be 3, right? 5 minus 2 is equal to 3, so it ends up being beneficial, right? What matters is the rewards combined, the deltas combined, not the delta of a single individual number, right? Which is why I don't filter out here negative deltas because again they could be part of the solution, right? But that's essentially what I do. So essentially I get the quote-unquote reward or delta of every single number, slap it into a max heap, and then it's like, okay, we can only do it for 2 nodes at a time, so let's grab the 2 biggest rewards, add them together. If the reward is bigger than 0, then add that to my result and keep going, right? Otherwise, if it's less than or equal to 0, break because there's nothing less to see, return the result, and there we go, bada bing, bada boom. We have a reasonably efficient working solution to this problem, and yeah, but otherwise, that's pretty much it for this video. If you did find it useful, enjoyable, and able to perform, I'd highly appreciate if you left a like or a comment. But otherwise, I'll catch you next one. So till then, ciao, ciao, my friend. Bye-bye.